Welcome to the deep dive. This is where we take your sources, unpack them, and really pull out the key insights for you.
Think of us as your guides, helping you get straight to what matters.
And today, wow, we've got a really interesting study. It's all about tackling climate change by basically vacuuming CO2 right out of the air.
That's right. The full title, just so you have it, is Carbon Dioxide Direct Air Capture for Effective Climate Change Mitigation Based on Renewable Electricity. A new type of energy system sector coupling. Quite a mouthful.
Ah, yeah, definitely. So our mission today is to get into the findings of this specific study.
Exactly. We'll look at what this research says about direct air capture, or DAS, the energy it needs, what it might cost, its potential.
Especially when it's powered by renewables, right?
Yeah.
That seems key here. And they use the Maghreb region as a case study.
Precisely. It's a really focused look.
And this is super relevant, isn't it? I mean, we hear so much about cutting emissions, but actually removing carbon that's already up there is becoming critical.
It really is. And that's the starting point for this study. Why do we even need this removal stuff?
Yeah, why can't we just stop emitting?
Well, this paper makes it pretty clear. Hitting those climate targets, like the 1.5 or 2 degrees Celsius goal from the Paris Agreement, it's not just about future emissions anymore.
Because all the stuff we've already put up there.
Exactly. Our past and present emissions basically mean we can't hit those targets just by cutting going forward. We need what they call negative emission technologies, NETs.
Nets, okay. And this study actually puts numbers on that.
It does. It references other research, Kriegler et al.,
Yeah.
suggesting we need to pull out something like 10 gigatons of CO2 a year in the 2050s.
10 gigatons. That's a lot.
It's huge. And maybe even double that, like 20 gigatons later in the century. The scale is just staggering.
Right. So we need nets. And this study focuses on direct air capture, DAC, calling it one of the most promising options.
Yes. And that's interesting because, a lot of the big climate models, the integrated assessment models, or IAMs, they've often leaned heavily on something else, BECCS.
BECS, Bioenergy Carbon Capture and Storage.
That's the one. But this study argues BECCS has some serious hurdles.
Like what? What's the problem with BECCS according to this paper?
Well, they list quite a few things. Huge land requirements for growing the biomass, for starters.
Okay.
Potential water stress, conflicts over water use. It doesn't give a great energy return compared to other sources. And then there are societal barriers, public acceptance, land use competition.
So it's complicated.
Very. Plus, the study points out BECCS is often seen as a kind of baseload power source, which doesn't fit so well with future energy systems that'll be dominated by variable renewables like solar and wind. They need flexibility.
Ah, okay. So that context helps explain why this study is looking so closely at DHEC powered by electricity, especially renewables. It might be a better fit for the future energy system.
That seems to be the argument, yes. It's maybe an alternative that hasn't been fully baked into some older models.
All right, let's dig into DT itself then. Based on this study, what exactly is it? How does this tech work?
So the paper specifically models these low-temperature solid sorbent DC units. Think of it like a big filter or a chemical sponge.
A sponge for CO2.
Kind of, yeah. A special material, a sorbent, grabs CO2 molecules from the air at normal temperatures. Then, to release the CO2 so you can capture it, you heat the material up.
How hot are we talking?
Around 100 degrees Celsius, according to the study's parameters, so not crazy high temperatures. It's called temperature swing adsorption.
And that process needs energy.
It does. It needs electricity to run the fans and systems, and it needs that heat, around 100 degrees C, for the release step. The study mentions companies like Climeworks, Global Thermostat. They're already working on or running plants like this.
Okay. And what makes DC attractive, according to this study? You mentioned flexibility, but what else?
Several key things. One big one is land use. It has an excellent area footprint, meaning it needs way less land than BACCS for the same amount of CO2 removal.
So less competition for farmland.
Exactly. And because it just needs air, you can potentially put these plants on, like unused desert land or degraded land. The study says no major conflicts with land use.
Okay.
And the third point, which is really central to this paper, is that it's an excellent match for a future energy system based on renewables.
Right, which brings us to the Maghreb. Why did this study zoom in on that specific region?
Yeah, the rationale is clear in the paper. The Maghreb, Morocco, Algeria, Tunisia, Libya, it ticks a lot of boxes.
Like,
It enjoys abundantly available, low-cost renewable energy resources,
right.
especially solar, just massive solar potential. And critically, it has vast tracts of unused land.
Desert, mostly.
A lot of it, yeah.
Yeah.
Perfect for big solar farms without bothering anyone.
Okay, this is where it gets really interesting for me. How does this study see these DIAC plants being powered there? What's the energy setup?
The model is all about sustainable operation. So the energy supply is designed to be mainly based on low-cost renewable electricity and heat pumps for the heat supply.
Heat pumps, like in a house.
Similar principle, but industrial scale. They use electricity very efficiently to generate that 100-degree heat needed for the DIAC process and the electricity itself. The study's broader energy analysis for the Maghreb points to a future dominated by solar PV with some wind.
So lots of solar panels.
Tons of them.
Yeah.
The DIAC power source basically mirrors the region's overall projected clean energy transition. It fits right in.
And the modeling sounds pretty detailed, not just back of the envelope stuff.
Oh, no, it's sophisticated. They did full hourly modeling for the Maghreb region, and with high spatial resolution, like a detailed grid map to really understand the resource availability hour by hour, location by location.
Wow.
Yeah, the model includes different types of PV, fixed tilt, single axis tracking, onshore wind, batteries for storing electricity, those electrical heat pumps we mentioned, and also thermal energy storage, TES, to store the heat.
Storing heat. Why?
It helps buffer the heat demand. You can generate heat when electricity is cheap and plentiful from the sun, store it, and then use it later, maybe when the sun isn't shining. It helps smooth things out and reduces how big the heat pumps need to be.
Clever. And did they estimate the energy needed per ton of CO2?
They did, based on their 2050 projections and assuming a heat pump efficiency, a coefficient of performance, or COP of 3.
COP of 3, meaning you get 3 units of heat out for every 1 unit of electricity in.
Exactly. With that, they estimate needing, on average, 182 kilowatts of electricity and 1,102 kilowatts of heat for each metric ton of CO2 captured.
That's still quite a bit of energy. So how do you make that work reliably and cheaply with solar, which obviously isn't on 2047?
That's the multi-billion-dollar question, right? This study's answer revolves around cost optimization and storage. They found that because solar PV and batteries are expected to get so cheap,
Yeah.
the most cost-effective system relies heavily on solar. Very high solar PV electricity supply shares.
But the nighttime gap.
Yeah.
How do you keep the DS running?
Batteries and thermal storage. They are absolutely crucial. The modeling in the study show that around half, 50% of the electricity needed by the DK system components actually comes from discharging batteries.
So charge batteries during the day with excess solar, use battery power at night.
Exactly. And the thermal storage helps manage the heat side.
And the study emphasizes running the DK plants almost constantly.
Yeah.
High full load hours.
Yes, that's a key finding for cost effectiveness. Getting high DAKE FLH, or full load hours, is vital to minimize the overall cost per ton of CO2. You want those expensive DAT machines running as much as possible.
Okay, makes sense.
The model optimizes for this, showing the best cost comes when the DAC units and the heat pumps run around 8,300, 8,400 hours a year.
Which is also a little bit almost all the time, like 95% of the year.
Pretty much, near base load operation. And it's the battery system storing that solar energy that make this close to base load generation of energy supply possible, even though the primary source, solar, is intermittent.
But the study also mentioned flexibility, right? It doesn't have to be base load.
Correct. The optimal cost pushes towards near base load, but the system can be flexible. The DACHP units could ramp down if needed. The TES acts as a heat buffer, batteries store electricity, and interestingly, the model even includes some curtailed electricity.
What's that? Throwing away power.
Sort of. It means sometimes it's actually cheaper overall to build a bit more solar capacity than you strictly need at every moment, and just not use some of it during peak sun hours. This ensures you have plenty of cheap energy to maximize the runtime of the DSC units, which is the main goal for low costs. A little bit of curtailment is part of the optimized system design in the study's results.
Fascinating. Okay, let's talk money. What did this study project for the cost? The LCAH.
Right, the levelized cost of CO2 BAC. That's basically the all-in cost per ton captured over the system's lifetime.
And the numbers.
For the best sites in the Maghreb, those with potential for multiple gigatons per year, the study projects around 70 euros per ton of CO2 in 2040, dropping to about 55 euros per ton in 2050.
55 euros. That's quite low compared to some numbers you hear.
It is. It represents a substantial cost reduction projected over the next couple of decades.
And do they break down where that 55 euros comes from?
Yes, they provide a breakdown for a 1 GTCO 2-year system in 2050. The DT units themselves are the biggest chunk, about 44.6%. Then you have the heat pump system at 16.3%, the solar PV plants at 16.1%, batteries at 15.3%, thermal storage at 7.2%, and a tiny bit from wind, 0.5%.
Well, the DDC machine itself is still almost half the cost.
In that 2050 projection, yes, but the energy components, PV, batteries, heat pump, are also really significant chunks.
Is 55 euros per ton realistic, though? Where does that compare?
The study addresses this. They mention companies like Carbon Engineering aiming for below 100 euros per ton eventually. So this 55 euro figure for 2050 is presented as being within the expected range if things scale up quickly and the technology learns as expected.
Learning curves, basically.
Exactly. The cost drop relies heavily on two things, according to the study. First, much cheaper energy, especially from large-scale solar PV at prime locations. And second, big reductions in the capital cost the upfront price tag of the DSC units, the batteries, the heat pumps, etc., as we build more and more of them. Standard industrial learning curve effects.
Okay. And the potential scale in the Maghreb, you mentioned gigatons.
Yeah, the numbers in this study are staggering. They estimate the potential annual capture in the region could rise from 131 GTCO2 in 2040 to 155 GTCO2 in 2050.
Wait, 155 gigatons? Didn't you say the global need was maybe 10, 20 GTCO2?
I did. That's the point the study makes. The potential in just this one region is calculated to be roughly one order of magnitude, like 10 times greater than the estimated total global demand for CO2 removal by mid-century.
Wow. So the resource potential isn't the bottleneck, at least not there.
Doesn't look like it, according to this analysis. And this is even with a constraint they applied, limiting renewable energy plants to just 10% of the available land area.
Okay, but what about that land area? Even if the potential is huge, does capturing, say, 1 gigaton take up a massive amount of space?
That's another key point the study tackles head-on. For 1 GTCO2 per year, which, remember, is a big chunk of the global need, they estimate the total land footprint for everything, PV, wind, DAC, heat pumps, storage, is about 5,244 square kilometers.
Which sounds big.
It does, until you compare it. This study calculates that this area is only 0.08% less than 1/10 of the total Maghreb land area.
0.08%.
That's it. That's the number. So their conclusion is that even for a really significant contribution to global CO2 removal, the land requirement is negligible in the context of the region's available, often unused land. The land use argument against DAC, at least based on this analysis for this region, seems quite weak.
That really reframes the discussion. So looking bigger picture, what does this study say about the overall energy system implications?
Well, it doesn't just look at DA in isolation. The paper also models the broader energy transition for the Maghreb countries, moving to 100% renewables by 2050.
And is that feasible?
Their analysis finds it's technically feasible and economically viable. They project the region needing about 200 gigawatt of installed capacity, mostly solar and wind, and the overall cost of electricity, LCOE, for the whole system dropping to around 50 euros per milliwatt by 2050.
Okay, 50 euros per milliwatt for the whole system. How does the cost of power for the DC plants compare?
This is interesting. The study finds the specific energy supply cost for the DET plants running near baseload at the best sites is actually lower, around 30 to 33 euros per milliwatt in 2050.
Lower than the grid average. Why?
Two main reasons given in the study. First, you cite the Renewable plus Renewable system at the absolute best spots for sun and wind, optimizing for cost. Second, the DRC system has a very steady, predictable near baseload demand, which is inherently cheaper to supply with renewables and storage compared to matching a country's fluctuating overall demand curve.
Got it. And the sheer scale of energy needed for DC could be huge.
Potentially massive. This study estimates that if the Maghreb supplied the energy for just 5–10% of the global CO2 removal need, the electricity demand just for DAI in that region could end up being about the same size as the demand in the power sector, or possibly even the same size as the total energy system by 2050.
Wow. So DECI could become a whole new massive consumer of clean energy.
Exactly. That's why the study talks about carbon removal potentially becoming a new energy sector, driving huge investment in renewables.
A powerful synergy. Okay, you mentioned the baseline cost getting down to 55 euros.
Yeah.
But did the study look at getting even lower?
It did. They ran some sensitivity analyses. If the costs of the key component, the D-Day units, PV panels, batteries, thermal storage, fall even faster than assumed in the baseline,
Uh-huh.
that could shave off maybe another 40% from the LCOD. And then if international cooperation leads to lower financing costs, say a lower WACC, weighted average cost of capital, down to maybe 5%,
Right.
that could knock off another 10%. Add it all up, and in their most cost-optimized but possible case, they suggest costs could potentially reach levels well below €30 by 2050.
Below 30 euros? That'd be incredible. But what's the catch? What are the risks this study points out that could stop us getting there?
The biggest one they flag is deployment speed. The major risk is identified as a too slow market deployment of DAC technology.
Meaning, if we don't start building these things fast enough.
Exactly. If the market grows too slowly, you don't get those learning curve effects, the cost reductions from mass production and experience. If deployment is sluggish, the study suggests 2050 costs might end up being much higher, maybe only reaching the levels they otherwise expected around 2030.
And that deployment speed might depend on other sectors too.
Yeah, they link it partly to how quickly other sectors decarbonize, like transport or chemicals. If those sectors create demand for products made from captured CO2, like synthetic fuels, that could help pull the DAC market forward faster in the early days.
Makes sense. What about storing the CO2 once it's captured? Does the study mention that?
It touches on it briefly. It acknowledges concerns about the long-term safety of storing CO2 as a gas underground, potential leakage risks that other studies have raised.
Right.
The study suggests that ensuring truly permanent safe storage might eventually require converting the CO2 into solid mineral forms. That would add energy and cost, but they state it's likely indispensable for responsible long-term carbon storage.
But that's not unique to DASI.
Yes. No, exactly. The study is clear that this long-term storage challenge applies to all carbon capture methods, not just DASI. It's a separate, vital piece of the puzzle for the whole CCS-CCU industry.
And finally, do they stress the need to start now?
Absolutely. There's a clear statement. The presented cost levels in 2040 and 2050 could be achieved only if the implementation of CO2 capturing technologies starts in rather small scales in the 2020s in order to stimulate a learning curve.
So we need to get moving soon to hit those lower costs later.
That's the message. Delay means higher costs down the line.
Okay, let's try to summarize the big takeaways from this specific study.
Sure. I think number one is that meeting climate goals absolutely requires large-scale CO2 removal alongside cutting emissions. Can't do one without the other, really.
Okay.
Number two, data looks like a really promising way to do it based on this analysis. It's efficient with land, doesn't conflict much with other land uses, and critically, it pairs really well with cheap renewable energy.
Right.
Three, regions like the Maghreb have just phenomenal potential, according to this study. Enough potential to meet global needs many times over, powered by their renewables, with costs projected to fall significantly, maybe to €55 per ton baseline by 2050, possibly much lower, and all with very small land use impacts.
And it supports the broader energy transition too.
Yes. Number four is that the transition to 100% renewables is found to be feasible and affordable, and DAY actually fits neatly into that, potentially becoming a major new energy demand sector that drives more renewable deployment.
So the big strategy implied by this study is a twin push. Rapid renewables build out and scaling up nets like DATI, starting now.
That's the core message. And number five, maybe, is that for regions with the right resources, like the Maghreb, this isn't just a climate necessity. It could be a major economic opportunity.
A new clean industry. Okay, lots to think about there. So maybe a final thought for our listeners based on this study.
Well, given the massive scale needed and the study highlighting slow deployment as the biggest risk to getting costs down, maybe the question is, how do we actually ensure deployment happens fast enough globally? Who pays for that initial scale-up, especially if the costs are higher at the start?
Yeah, who bears that responsibility? Or another angle, thinking about that storage issue the study touched on.
Right. If capturing the CO2 is only half the battle, and truly permanent storage might require extra steps like mineralization, what's the next big R&D push needed there? Solving the capture is great, but we need the whole chain to work reliably and safely long-term. What happens after capture?
Definitely critical questions. Well, this has been fascinating. Thanks for joining us for this deep dive.
My pleasure. Really interesting paper.
And our source today, once again, was the study titled Carbon Dioxide Direct Air Capture for Effective Climate Change Mitigation Based on Renewable Electricity, a New Type of Energy System Sector Coupling.